Hello friends, in today's video lecture, I explain about modular function. Here modular function is a mathematical function that using cryptography for convert plaintext into a ciphertext and vice versa. And after then I explain about the extended Euclidean algorithm. Extended Euclidean algorithm is required to calculate the inverse modular function. An inverse modular function is needed when we convert ciphertext into a plaintext, means inverse of plaintext into a ciphertext. Objective behind study the modular function and extended Euclidean algorithm is KWL. K means what you know before studying modular function and extended Euclidean algorithm, so that basic or fundamental knowledge of cryptography is required before studying modular function and extended Euclidean algorithm. What you want to know? The detail of mathematical function that use in ciphers, cryptography, algorithms for conversion of plaintext into a ciphertext and a ciphertext into a plaintext. L. What you will learn after studying modular function and extended Euclidean algorithm. So, how to apply and use mathematical function like field, ring, group, modulo, inverse function in cryptographic algorithm, and also know the properties of field, ring, group, and where we use and how to satisfy all the properties. So it's a modular function or a not. So before starting the depth of modular function, we study about the number system, or we differentiate different numbers. First one is prime number. Prime number is an integer or a whole number that has its only factor of 1 and itself. It means prime number is divisible by 1 or itself. So for example 2, 3, 5, 7, 11, 13, 17, 23 and 127 all are the prime numbers. Whole number are simply the number 0, 1, 2, 3, 4, 5 and so on. But numbers like 1 divided by 2, 1.1, 2.3, 13.7 are not a whole number, because whole number not considered or allowed a fractional number. Counting numbers are a whole number, but counting numbers does not allow 0. So 1, 2, 3, 4, 5 are the and so on are the counting number. Integer number are like a whole number, but they include positive number and negative number both, and also 0 include in integer number, so that minus 10, minus 8, minus 5, minus 2, minus 1, 0, 1, 3, 5, 10, all these are the integer number. So integer number can be a positive and negative, or maybe a 0, but fractional number not allowed as a not considered or allowed as a integer number. What is modular arithmetic? Actually, sometimes modular arithmetic also called a clock arithmetic in a simple language. So modular arithmetic is basically doing operation like addition and multiplications, not on a line as usually we use or we do in daily life, but on a circle. The values wrapped around, also staying less than a fixed number called a modulus. For example, 39 mod 7. When we simplify 39 mod 7, then 39 divided by 7. So 7 divide 39 5 times completely, so 5 is a divisible value, and here 4 is remainder. So 39 mod 7 equals to 4. It means the remainder value is considered as a modular value or mod value. So here when we calculating this function, according to this figure and clock cycle, then here 25 is a fixed value. So after 25, 0 is considered as a 26, 1 is considered 27, 2 is considered 28, 3 is considered 29, and 4 is considered 30. Similarly, all values are considered, and then this is completely divisible. After remainder is any value is remainder, then this value is considered as a modular arithmetic. When we performing addition in modular arithmetic, then same as on the number line. For example, add 15 and 18 using conventional arithmetic or number line. So start from 0, then 0 to 14 are 15 element, and 15 to 33 there are 18 element. When we join both or add both, then 0 to 33 means the addition of 15 plus 18 is 33 according to number line, but given in figure. But according to circular line or a modular system, here the output is 7, because 0 to 14 is 15 element and 15 to 7 is 18 element. So the output is 7, because after 25, 26 is 0, 27 is 1, 22, 28 is 2, 29 is 3, 30 is 4, 31 is 5, and similarly on. Similar multiplication works in the same fashion. 7 into 4 equals to 28 according to number line, but according to modular system or a circular line, the output is 2. Here I put one question for you. This question you solve according to modular system. So you design a clock and then resolve this question. Question is, you go out at 10 p.m. and return back after 4 hours. At what time do you return? This question is similarly solved according to a clock or a alarm values. Actually, modular arithmetic is not unfamiliar to us. We have used it before when we want to calculate. For example, when we would like to get up in the morning, if we want to get a certain number of hours of sleep. Say we have planning to go bed at 10 p.m. and want to get up 8 hours of sleep. To figure out when to set our alarm for our count, starting at 10 the hours until midnight, and midnight you raise to 0 and keep counting until our total is 8. The result is 6. What we just did is to solve 10 plus 8 equals to 20, and 10 plus 8 equals to 18, and so it's a 18 mod 12. As long as you don't want to sleep more than 12 hours, you will get the right answer using this technique, because 18 divided by 12, then there is 6 is remainder, and we get up on 6 a.m. So Similarly, I put one question for you. What happens if you slept more than 12 hours? Please solve this question. Next, to do modular addition, we first add the two numbers normally, then divide by the modulus and take the remainder. For example, 17 plus 20 equals to 37. So, 37 mod 7 equals to 2, or we can represent this into 17 plus 20 mod 7 equals to 37 mod 7 equals to 2. Now, what is canonical representation? Let's n be a modulus. If a subset of Z is given, then there is an AC subset of Z with AC residue E mod n. And here AC lie between 0 to n minus 1. And AC is called canonical representation of A. So, here I put some examples. Examples are n equals to 3 and a equals to 2. Then what is AC equals to? So, here 12 mod 3. 12 mod 3 equals to 12 divisible by 3 times, and remainder is 0, so the value of AC is 3. Similarly, n equals to 4 and a equals to 15, then 15 mod 4, then it's completely divisible by 15 divisible by 4, it's 3 times, but 3 is remainder. 3 divisible by 4 and 3 is remainder, and so AC equals to 4. Sorry, in first question remainder is 0, so the output of AC is 0, because 12 mod 3 equals to 3. 12 mod 3 equals to completely divisible by 3 times, so the remainder is 0, so AC equals to 0. And in second question, n equals to 4 and AC equals to 15, then AC equals to 4, because 15 mod 4 divisible by 15 mod 4 divisible by 4, then 3 times it's divisible and remainder is 4. So now third question is n equals to 11 and a equals to minus 6, then what will be the output of AC? And you calculate according to same this formula. So minus 6 mod 11. So how do you calculate the output of this? So you calculate the output of third question similarly before. Now next, after few lecture we study about the elliptical curve, and now we study about the cryptography. In cryptography we study about the ciphers, and in further lecture we calculate plaintext into a ciphertext and ciphertext into a plaintext. So there is different properties, and algebraic mathematics is required for that. So algebra refreshers is here. In order to speak about the cryptography and elliptical curve, we must treat ourselves to a bit of an algebra refresh. We will concentrate on the algebraic structure of group, ring and field. Groups. A group G is a finite or infinite set of elements together with a binary operation which together satisfy the four fundamental properties of closure, associativity, identity, property and inverse properties. Abelian group. Abelian group have one extra property rather than group properties. So, abelian group have 5 properties. First one is closure, second associativity, identity, element, inverse, and last one is commutative group. Ring. A ring is a set of S together with two binary operations plus and addition and multiplication respectively, satisfying the following condition. A ring is a abelian group under addition, multiplication, associativity for all ABC subset of S, and left and right distribution for all ABC subset of Z, and fulfill out these properties. Next one is field. A field is a set of elements which satisfy the field axiom for both addition and multiplication and is a commutative division algebra. For example, commutative property, associativity, distributive, identity and inverse for addition and for multiplication. So you in commutative A plus B, in multiplication A into B, similar equals to all are calculated here. Now next is division algebra. A division algebra is a ring in which every non-zero element has a multiplicative inverse, but multiplication is not commutative. Like ring, a division algebra is a set of S together with two binary operations plus and multiplication satisfying the following. Plus and multiplication satisfying the following. Associativity over addition and multiplication, commutative over addition, identity element for addition and multiplication, inverse for addition and multiplication, left and right distributive, and one most important is fields are divisible. Fields are division algebras with the additional features of being commutative over multiplication. Here, modulus of n addition multiplications. Example of modulo 8 additions modulo 8 multiplications. When we solving this, so all these things are depend on that particular symbol. If we calculating modulus 8 of multiplication, then there is multiplication symbol. If we solve modulus 8 addition, so there is addition symbol. So how to calculate? According to addition, there is value is changed. How? 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 2 is 2. 0 plus 3 is 3. 3, 4, 5, 6 and 7 similarly. Similarly, 1 plus 0, 1. 1 plus 1, 2. 1 plus 2, 3. Similarly, 4, 5, 6, 7 and here 7 plus 1, 8. It means 8 modulus 8 means 8 divisible 8 divided by 8, so remainder is 0. Here similar 2 plus 0 is 2. 2 plus 1 is 3. 2 plus 2 is 4, 5, 6, 7 and 6. 2 plus 6 is 8. Then again 8 modulo 8. Remainder is 0, and 7 plus 2 is 9. 7 plus 2 is 9, then 9 divided by 9 modulo 8, then remainder is 1. Similarly, we calculate all fields of this table. So, how to check this modulo 8 is abelian or not? For this, we first match if top row elements are exactly matched with any row of this table, then we identify the identity element easily. So 7, 6, 5, 4, 3, 2, 1 and 0. Top element row is similarly matched with first row of this table. So this element is called an identity element. It means 0 is an identity element of this table. So we find 0 in each row. If this 0 is exist in each row, then this satisfies the property of inverse. So if this is satisfy the property of inverse, then we check associativity and commutative property. And if the value of this table is lesser than or equal to 7, then it's also satisfy all these property, because when we talking about the mode function of 8, it means the value lie between 0 to 7. If the value is greater than 8, then it doesn't satisfy the commutative property. And in addition and in multiplication, natural number, there is commutative and additive and distributive properties followed by each and every number. But here we classify its abelian or not according to the inverse property and identity element. If we find identity element and identity element is found in each row, then it's follow the inverse property. But if identity element is doesn't match with a single row or more than one row, then abelian property is not satisfied by that. Similarly, if modulo 8 addition and we calculating multiplication, then this plus symbol is convert into a multiplication, and whole these values are also changed. How? 0 0 into 0 0 0 into 1 0 0 into 2 0, and similarly 0 0 0 0 0. Similarly 1 into 0 0 and 1 into 1 1 into 1 1 and 1 into 2 2. Similarly 3 4 5 6 and 7, and 2 into 0 0 2 into 1 1 2 into 2 4 2 into 3 6 2 into 4 2 into 4, then 8, and 8 modulo 8 equals to remainder is 0, and 5 into 2 10 modulo 8 10 modulo 8 equals to remainder is 2, and similarly remainder is 4 and 6. So like all values of this remaining table, you will calculate remainder values calculated. And after then, similarly first we check top row elements match with which row. Here in this table, this top row similarly match with second row of this table. So the identity element is 1. Here identity element is 1. And now we check this identity element is present in each row of this table. Then in first row, the value of 1 is not available because all values are 0. But so that if any row is not occupy the identity element, then abelian property is not satisfied by this function. Now next is extended Euclidean algorithm for integer. Extended Euclidean algorithm is required to calculate the inverse modular function of any number. So here input value and output value. In input, positive integers a and b with a less than equal to b, and output d equals to greatest common divisor of ab, and integers x, y satisfy the equation ax plus by equals to d. Then the extended Euclidean algorithm will be solved. So here there are 5 steps to solve this algorithm. Here the value of a is assigned to u and the value of b assigned to v. Similarly, a assigned to ax, 0 assigned to yx, and 0 assigned to ax2, and 1 assigned to y2. And this loop is until going when u equals to 0. So v divided by u assigned to x and value of v minus au assigned to r, and the value of x2 assigned x2 minus ax1 assigned to x, and the value of y2 minus qy1 assigned to y. Similarly, the value of v assigned to u assigned to v, and the value of r assigned to u, and the value of x1 assigned to x2. Similarly, x assigned to x1, y1 assigned to y2, and y assigned to y1. And in fourth step, the value of v assigned to d, x2 assigned to x, and y2 assigned to y, and return value is dxy. The algorithm terminates when u equals to 0, in which case v equals to greatest common divisor of a and b, and x equals to x2 and y equals to y2 satisfy the ax plus by equals to d. Then inverse extended Euclidean algorithm is solved. Now inverse using extended Euclidean algorithm. The inverse modular function, how to calculate using extended Euclidean algorithm. In this, input is prime p and a is subset of a and p minus 1. So output is a minus 1 mod p. Here there are 4 steps. In first step, the value of a assigned to u and p assigned to v. In second step, the value of 1 is assigned to x1 and 0 is assigned to x2. And this loop is terminate when x equals to 1. So, this loop is terminate when u equals to 1. So here the value of v divided by u assigned to q, and v minus qu assigned to r, and x2 minus qx1 assigned to x. Similarly, u assigned to v, r assigned to u, x1 assigned to x2, and x assigned to x1, and return is x1 mod p. Thank you friends. In next video we study about the different ciphertexts. In different ciphertexts we calculate plaintext into a ciphertext and ciphertext into a plaintext. So we use modular function and extended Euclidean algorithm for the conversion of plaintext into a ciphertext in next video. Thank you.